Hi, everyone. Today is the 13th of January, and we are back from the winter holidays. And I'm very happy to welcome Matthias Hall-Andersen, who is a zk researcher and co-founder of zkSecurity company, which does security auditing and engineering with advanced crypto and zk proofs, as Matthias's website says. So today, Matthias will be presenting a paper on Extractable Witness Encryption for KZG commitments and efficient Laconic OT. Yeah, not further ado, thanks, Matthias, and take it away.
Thank you. Yeah, this is joint work together with Niels Fleischhacker and Mark Semkin. And this was a paper at Asia Crypt of last year. So before we actually get to sort of the core of the talk, let's start by recalling how KZG commitments work. So obviously the title has KZG commitment in it, and it will be sort of instructive to sort of just recall for ourselves how exactly KZG commitments work and sort of why they work just as importantly. So a KZG commitment is a type of polynomial commitment. You have some polynomial in a field of some degree. And KZG commitments are basically based on the following set of observation. The first one is that if at some particular alpha, my polynomial value is beta, then obviously if I subtract beta from the polynomial, it's 0. And that means, in other words, it has a root at alpha. And so if I can divide out x minus alpha, it divides the polynomial. And now this means that there exists some quotient polynomial q, such that q times x minus alpha is f of x minus beta. Okay, by the way, if at any point you have any questions, just feel free to stop me. I would prefer to do this in a slightly interactive way. And that means that the probability, sort of by spot simple, if the probability over random tau, if I check this relation over random tau, if the probability is greater than d over field size, then it means that such a Q exists. Okay. And so the idea behind KZG is that, hey, then I'd simply take this probabilistic statement here, and I fix some tau, and I use a bilinear pairing to check this multiplicative relation over the field. So I have this multiplicative relation over the field. And thankfully, I have this wonderful tool called a bilinear pairing that allows me to check exactly one multiplication. So I'm good. Here, the notation, maybe for those who are checking in and not familiar with the notation, this means it's an element in G1. So it's G to this quantity, and this is, well, G to 1. And again, this is an element in G1, and this is an element in G2. And the pairing lands up in some target group. So, as I said, yeah, you fix some tau, and by fixing some tau, so you sort of flip the probability statement around. You say instead of sampling an f and then checking for a random tau, I fix a tau, and then I have this non-interactive check using a bilinear pairing. And what this allows me to do is, if I recompute the powers of tau like this, then I can compute the quantities inside these brackets homomorphically from this. But obviously, one observation that we just had is that, hey, you can pick this f and this q adaptively based on the commitment key, right? So obviously, if I gave you tau without putting it inside these wonderful little brackets, without like raising it to the exponent in G1 and G2 respectively, then you could simply pick a polynomial for which this is true. This statement is true, say for a single tau, but for which this quantity is not true over the integers. So it is not immediately obvious why KZG would actually be secure. So this is just to recall the entire scheme. There's nothing going on here except what we already went through. Again, the evaluation proof is simply the commitment to this quotient polynomial. Okay. So what do we mean by secure, and like what do we mean by why we would believe in KZG? Well, in this case, the notion that we want is an extractability notion that says that if you have an efficient adversary, some algorithm that produces a commitment and an opening proof for alpha beta, such that it verifies, then there also exists some other efficient algorithm, such that when I give the algorithm access to A's code, then it can recover the polynomial, such that the polynomial at alpha evaluates the beta, and the polynomial is sort of inside the commitment. If I recommit to the polynomial, I get the commitment. This is not a hiding commitment in this case. It's a slightly naive definition, but so be it. So the intuition behind this is that sort of if you can provide a valid pi, then this is sort of equivalent to knowing f of x, because there's like an efficient way of recovering f of x, satisfying that it's a preimage of the commitment, and the particular preimage at alpha is also beta. This is combined with like some binding notion for the commitment usually. So it's sort of saying, hey, it's not vacuous to recover an f. In other words, if you recover two different f's, then you would break binding of the commitment, usually some cryptographic assumption. Okay.
Sorry, but maybe just to linger for a few seconds more in the previous definition. I assume you hide the details about the randomness in the commitment under the rug a bit.
In this case, it's a non-hiding KZG commitment. What I've been describing so far is a non-hiding KZG commitment.
Okay.
Yeah. And actually, throughout all of this, the commitments won't be hiding. There's sort of an interesting caveat that, like many commitments, what the extractor will recover will actually not satisfy that when you commit to it, you will get the original commitment, even if it has randomness. For instance, if you have a Fry-based commitment, the extractor will not be able to recover something that when you recommit to it, you will get the commitment itself, because the commitment might be computed maliciously. For instance, I could just pick one leaf in my Merkle tree, set it to complete foobar, and in that case, you will never be able to recover that leaf, the preimage of that leaf. Yeah. So this is a naive definition. It's not hiding, and it doesn't work for every polynomial commitment scheme, but it's like it's a very strong definition actually. Everybody okay? I'm assuming that's a yes. Okay. So we want to prove this notion. Unfortunately, sort of regular falsifiable assumptions won't do. So what we're going to do is that I'm going to introduce a model called the algebraic group model, which basically says that we restrict the class of adversaries. So we say, now, here I said that every efficient adversary, that means that it's like some adversary that runs in probabilistic polynomial time in the security parameter, blah, 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 blah. But what I'm going to say is I'm going to consider a special class of adversaries, namely what we call algebraic adversaries, which are adversaries that whenever they give me a group element, so the adversary runs for some time and he gives me a group element, then that group element can be described as a linear combination of group elements previously provided to him. So he gives me some element delta, but then he also gives me a vector of scalars such that when I take the group elements that I gave to him and compute the combination with these scalars, I get delta. So he explains everything that he's giving to me. And the intuition is that he's kind of an adversary that can only do kind of naive things, right? Like the only thing that he really do is like compute sums of group elements, like raise them to scalars. In some versions of the model, he can like ask for a totally random group element. He will get that. Slightly more formally, assume now that we have like a symmetric pairing, because in a security proofs we're going to look at symmetric pairings, because if I have a scheme that is secure in a symmetric pairing setting, then it's also secure in an asymmetric pairing setting, simply because I'm restricting what the adversary can do. So for simplicity, and also because it strengthens all the results, which is going to, whenever we do security proofs, we're going to do them for symmetric pairings. because it admits more power to the adversary. Okay. So suppose that we give an adversary some set of group elements T1 to Tn and some set of target elements T1 or to Tk. Then an algebraic adversary is one that if he produces some delta in the pre-image group, then he also provides some set of scalars such that delta is recovered as a linear combination of the group elements from G1. Now, if the element is in the target group, he has some more power, right? Like obviously he can compute linear combinations of the target group elements, but he can also pair any set of these group elements, right? He can just like take G1 and pair it with G8. That will get him some target group elements. So we gotta at least capture that to be somewhat plausible. So in this case, he provides a set of scalars that he combines the target group elements, and then he can also provide a set of scalars for the pairings between source group elements. Right. So this is a weakening. We're saying, hey, it's a particular class of adversaries that will explain everything we get from him, every group element. So in particular, right, he can't like take a bit of a group element and like, I don't know, compute some crazy hash function of something and return it to us. Like we're basically assuming that any such adversary wouldn't help. Like this should capture all the set of attacks that we care about. Any questions at this point?
Sorry, I might ask one. So I might have missed the type 1 remark. So in this particular case, we don't really ask the adversary to explain any elements in G1 and G2 separately.
Yeah.
Because we can just kind of, well, it would be the same to explain it separately and to explain the pairing from them at the same time, because there's homomorphism in the two.
Yeah, you could have a version of this of the algebraic group model where you distinguish between, say, G1 elements and G2 elements. That would be a weaker class of adversaries.
Okay.
So we are giving him more power, which shouldn't hurt, right? Like if I have some construction, right, I can always, that construction has G1 elements and G2 elements. I can always just say, hey, G1 elements, G2 elements, same. I'm in a type 1 setting. In that case, the construction is still complete, right? You can still encrypt or commit or whatever you're doing with the construction, but it might not be secure, right? We're saying here, if you do that, then it is still secure. So we are affording him more power. Okay. So we're also going to need some sort of cryptographic assumption, because like this kind of adversary could be true even in groups where this is trivial, right? Where like computing discrete log is like not hard. It's like, I don't know, it's the integers over addition or something, integers under addition or something like this, right? Then you can still have an algebraic adversary, but there's no crypto to break. So we have this assumption, which is going to be the only cryptographic assumption in this entire talk, which is LD log, which simply says that, hey, if I sample a tau for any adversary, alpha, adversary A, if I give him tau to the 0, tau to the blah, 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 as well as the corresponding 1 and tau in the second group, then the probability that he recovers this tau from this sort of power of tau setup is negligible. Sort of a generalization of discrete log. So any questions about this assumption? This should be okay. Okay, so as a warm-up towards the much more complicated argument that we're going to have later, let's look at how you prove that KZG is extractable. So suppose we have some adversary. Oh, this should actually have an alpha beta here. So this is, you have some adversary that takes a commitment key and he produces a commitment and an opening proof. along with alpha and beta. Since we assume that he's algebraic, right? This is a group element, and this is a group element in G1 and G1. And since he's algebraic, he must also output some set of scalars. We call them Q and F for reasons that will sort of become obvious. And we say that this group element pi is a linear combination of the Q scalars, and this group element com is a linear combination of the F scalars. Okay. So this just by the fact that he's algebraic, he must give us some vector of Q and F, such that this is satisfied. This is by definition. Any questions so far? Okay. So now, if this polynomial I recovered, if it's actually such that when I evaluate F at alpha, I get beta, then we're done. We just extracted what we wanted to extract, and everything is happy, like the extractor works. In other words, if f of x minus beta is q of x times x minus alpha, we're done, right? That means exactly that f of alpha is beta. Now, if it's not the case that this polynomial is equal to this polynomial, I can subtract them from each other. So let's start by observing that if pi is an accepting proof, then when I evaluate q at tau, I recover pi, right? Just by definition, right? This is the equation that must hold in the pairing. So when I evaluate q at tau, I must get back pi. Now, another thing that we can observe is that if I do the same thing for f at tau, I must get back the com, right? Like I must recover com here. So now, if I take these two polynomials, if I take these two polynomials that are not equal to each other, in other words, if I subtract them from each other, then they're not zero, right? Then when I plug in tau into this polynomial, I must get zero. This is the central point, right? That if this polynomial is not equal to this polynomial, then okay, first and foremost, if I evaluate each one of the sides at tau, they must be equal, but they're not equal as polynomials, which means that I can subtract them from each other, I get a non-zero polynomial. Yet when I evaluate the polynomial at tau, it is zero, which means that, in other words, I have a non-zero polynomial and tau is a root of it, which means I can simply factor g to recover tau as a root of g. And by that, I can break the LG log assumption. Okay? Is the proof strategy clear?
I will ask perhaps a question to keep the slide on. I assume that in the full proof of KZG, you would want to add some kind of oracle that gives the adversary the ability to create other KZG proofs, right? So you would need to have more elements shown to the adversary than just the SRS.
Yeah, but those oh, so you're talking about simulation soundness.
Yeah, I kind of want to not assume that the adversary only sees the SRS, but also adversary might see some other, some other KZG proofs, some other KZG commitments every now and then.
Yeah, but I mean, as long as he's not equivocating, asking us to equivocate on something, which is we're not proving that we can equivocate on the commitment, then everything else is just like a linear combination that we also know.
Yeah.
Yeah.
Makes sense.
So even if he is asking us to commit to some other polynomials, right, like we can just do that honestly and just give it back to him. Like at no point do we need to do a simulation of any sort, right?
Yeah, sounds good.
There's no zero knowledge here, right? Like that's usually how you think. Where you get yourself into trouble is that you have a simulator that can produce simulated proofs for, like, your polynomial encryption scheme or your SNARK. But then at the later point, you also require that the extractor can extract from new proofs, and so obviously the extractor must work in presence of the simulator. But in this case, there's no simulator, so there's nothing, no special power for the game. Okay. So keep this in mind, because we're essentially going to use the same proof strategy, but with something more complicated later. Okay. So now to the second part of the title, which is witness encryption. So what is witness encryption, if you haven't seen it yet? I'm going to explain it with analogy to public key encryption. So in public key encryption, right, you have some key generation algorithm that produces a public key and a corresponding secret key. And you can take your public key and you can put in a message and output some ciphertext. And if you take the ciphertext and you input it into decryption with the secret key, you recover some message. And if it's correct, this message should be equal to this message. Okay. This is hopefully not new to people. So what witness encryption says is, hey, what if you don't have a key generation algorithm? What it instead says is that as your public key, you're going to be using some statement. So you're going to have some relation, some NP relation. And as your public key is basically going to be a statement, and your secret key is going to be some witness. So in other words, I can sort of take my my statement. If I'm the encryptor, I can take my message and I can produce some ciphertext. And if you know a witness, any witness, potentially there are many witnesses. If you know any witness for this statement, such that X and W is in the relation, then you can recover the message. And so this is correctness. This is basically saying you can decrypt. And what security says is that if X is not in the language, so I don't know, X is a graph and there's no 3-color ring, W, then if I encrypt the message 0 and the message 1 for any arbitrary pair of messages M0 and M1, then the ciphertexts are indistinguishable. Okay. So it's kind of like public key encryption. I guess, yeah, it's exactly like public key encryption. Yeah.
Sorry, Matthias. Yeah, what kind of security guarantee do you have, like encryption property guarantees do you have for X that is in the language?
That X is not in the language?
No, but I want to know what happens if you, so how are ciphertext for two different proper instances? Yeah, what can you say about two ciphertexts corresponding to two proper instances in the language? Are they distinguishable under certain other extra conditions, or?
No, I mean, the distinguisher knows the statement X. And
I see. Okay. Oh yeah. Sorry. But where is the? Okay, but where is the INCPA happening on M0 and M1? That's my question.
So I mean, the adversary gets to give me M0 and M1.
Yes.
And I have some statement not in the language. Ignore for now how you verify this. And if I encrypt, M0, I have two games, two distributions. One in which I encrypt M0, and one in which I encrypt M1. And it says that the distribution of ciphertext in the 0 case and the ciphertext in the 1 case are indistinguishable, computationally indistinguishable. Exactly like you would have in public key encryption, right? You set up some public key, and you get to give me two messages, and I encrypt one of them.
I think that I'm not maybe getting something. Maybe in the public key case, the public keys are always valid. So what is I assume the concrete real world example of me using witness encryption is that I pick actually a valid instance to which I know the witness, right? And I encrypt something to you, and I want you to not know what I encrypted unless you know the witness. But my instance is valid, so my case would be the bottom case, but with as X in language. That's my confusion.
Yeah, I mean, you actually can't really formulate public key encryption as an instance of witness encryption itself, because oftentimes the language is trivial in public key encryption, which I guess that's exactly what you're pointing out, right? It's always a valid public key that you're encrypting through. It's not a perfect analogy, if that's what you're aiming
I think, yeah, I think we can go forward. At least I will probably get this question answered.
Okay, so this won't actually fully, like this thing that I just vaguely described to you, that won't really fully do. So that's because this is the relation of valid KZG opening proofs, right? Like you have a statement that is like some commitment, some alpha, some beta, and a proof. Oh, this should not be in existence here. And what it's saying is that this pairing equation holds. The problem is that this relation is trivial. The language is trivial, sorry, which means that for every commitment com alpha and beta, there always exists a pi. This means that this notion doesn't give us anything, right? Like, so there's no security guarantee here, because like X, the statement X here is like some commitment alpha and pi, and there always exists some W, namely an opening proof, such that it's in the relation. So it's not. So the notion that I just showed is not enough if we want something non-trivial for KZG, right? Where our statements are going to be commitments and opening claims, and the witnesses are going to be KZG proofs. So we need again, like similar to when we define polynomial commitments, we're going to need some extractability notion. And we say that a witness encryption scheme is extractable, which is a stronger property, if there exists an extractor such that for any PPT adversary that distinguishes these two distributions, so in other words, the two distributions that we had before, with some non-negligible advantage, then the extractor is capable of recovering a witness with non-negligible probability. If you want a bit of an analogy, it's very similar to the notion of soundness versus knowledge soundness, where like soundness just guarantees that you can only be convinced of truth statements, whereas knowledge soundness guarantees that the prover or the environment intuitively knows a witness. Is this definition sort of clear? So like basically saying is, if you can win sort of the int CPA game with some non-negligible advantage, then from you winning the int CPA game, I can recover, in this case, a KZG proof.
I will again ask, what is X? What are the conditions on X here? Is X is X a valid instance here or not?
Everything is a valid instance. I mean, except in like the trivial case of like, oh, it's not a valid group element or something.
I see. Okay.
Everything is in the language. There always exists a pi. Like imagine you had an oracle that can compute discrete logs, right? Like you can always find a pi that satisfies this. Yeah.
So, like an analogy with this and the regular encryption would be that if you distinguish, you would extract a secret key, kind of.
Yeah, exactly. It's like it would be kind of like, hey, if you can distinguish the difference between like encrypting this thing with RSA or encrypting this thing and the other thing with RSA, then I can recover your RSA secret key or something like this. I can recover an RSA secret key. I can factor something like that. That will be the analogy. Okay. Okay. So actually, we're going to prove a slightly different primitive, but essentially the same. We're going to define this notion of an extractable witness chem. It's just sort of a convenience, because I don't want to deal with actually encrypting messages. So the only difference between a chem and a public key, or like extractable witness encryption, is that a chem encrypts a random message. And then obviously you can take your random message, you can feed it to a PRG and use the PRG to like encrypt your actual message, but it gives us like sort of a nicer separation of this primitive. So what does a witness chem take? Well, it takes a statement, and there's an encapsulation algorithm, and the encapsulation algorithm outputs some ciphertext, or encapsulated key, and then outputs the actual key. And then there's a decapsulation algorithm that takes a witness, and ciphertext and recovers the same key. Obviously, I can build like extractable witness encryption by just like stretching this K. Okay. And a very, very similar definition just says that you can't distinguish between me giving you a random key, a uniformly random key, or giving you the encapsulated key. So basically now I got rid of my messages, which is nice for simplicity. So now it says, hey, if I encapsulate X, I get a sort of key and a ciphertext, or I simply give you a random key, then you can't distinguish the real encapsulation from me just giving you a completely unrelated key. Okay, so if you wanted to try to construct an extractable witness chem for KZG, the idea is actually not that complicated. So the observation here is that on one side, I have something that the encapsulator can compute himself. Like if you're given a commitment, an alpha and a beta, you can compute this side by yourself. Right? There's nothing here that you don't know. You know the commitment, you know this beta, so you can put it in G1, and you obviously know one. Whereas this other side here, it depends on this pi that I want to extract, right? But crucially, these two sides are the same if the opening is valid. So I have something that the encapsulator, or the encryptor, can know, and I have something that the decryptor should know. Which means that sort of intuitively, I want to encrypt using one side of this equation, and then I want to decrypt using the other side of the equation. And this equation still holds, even if I lift both sides to some random r, right? Like if I take this side and I lift it to r, and I take this side and I lift it to r, the equality still holds. Right? I did nothing. So the intuition here is that now I can take now this thing is a random group element, right? Like this is some group element. It's if it's not the identity, then this is this group element to R is like something completely random, a random group element. And basically, I want that you can only compute this side if you actually know a pi. So you must know some pi that you sort of put into the pairing for you to recover this thing. So how am I going to do that? Well, for completeness, right, like the strategy is fairly obvious, right? I'm going to move this into this. I'm just going to move this R into the pairing. Now, obviously, if I write R times com minus a beta, the equation still holds. It's a bilinear pairing, so this moves in. And now this in theory is sort of a uniformly random group element. So what I'm going to do is, as I said, this is basically going to be my encryption key. I'm going to call this S. So encapsulation is going to pick a random R like this, and then it's going to compute this side of the equation. Okay, but in order for you to actually sort of compute this side of the equation, given that you have some pi, right? I need to give you some information about R, basically. So what am I going to give you? Well, I'm going to give you this part of R, right? So like if I give you this thing to R, you can sort of just pair this with your pi, and then you will recover this side. Right? So I'm going to move the R in here and pair. So that's just going to be the same. It's going to be the same as here. And then in order to give you sort of a little bit of a hint so that you can recover something in the target group that depends on R, I'm going to give you this tau in G2 minus alpha in G2, all of that times R. Oops. So my ciphertext is just this G2 element. And my encapsulated key, it turns out I want it to be a hash of S, because in a reduction, S is this thing is only going to be hard to predict, but it's some random group element of some distribution, and I want to recover a random like encapsulated secret. And then to decapsulate, right, you're just going to take this ciphertext and you're just going to pair it with the proof that you know. And after pairing that, you will recover the same S, and you just hash that, and that's your key. It's very, very, very simple scheme. Any questions at this point? We'll be modeling H as a random oracle. Okay. Okay, so why is this okay?
Sorry,
right?
sorry, I have a question actually.
Yeah.
Do I understand correctly that you cannot correlate K and CC? So if I'm seeing a ciphertext and K, it is kind of hard for me to tell. So from ciphertext, restoring S from ciphertext is hard.
Yeah. So if you go from the ciphertext, distinguishing K from a uniformly random bit string is hard, unless you know pi, right? Obviously, if you know pi, you can compute this pairing and you're golden. But if you don't know pi, then you should only be able to do it with negligible probability.
Yeah, okay, that makes sense. I guess I was not a bit confused by the notion of a camp, but basically you create the ciphertext and a K, and both assembled at the same time, and you cannot recover one from another. They're like two independent elements, unless you have the proof, in which case you can tell whether they are related or not. Okay.
It's kind of like a functionality that encrypts a random message, and then you can use that random message as your key. Yeah. Okay. So why is this okay, right? So okay, what do we want to prove? We want to prove that if you can distinguish, if when I give you a ciphertext, you can distinguish this thing from ciphertext and random bit string, then for some reason I can recover a valid pi. I can recover a valid KZG proof. That's my goal. So we're gonna limit ourselves to algebraic adversaries. So algebraic polynomial time adversary with access to this random oracle H. Okay. So suppose he has some non-negligible advantage, epsilon of lambda, right? Which means that the probability that he outputs the correct bit, right? Like there's the two distribution, either K0, in which case K0 is the correct that like CT is encapsulation of K0, or the bit is 1 and K1 is just a uniformly random bit string. And the probability that he somehow manages to guess which case he's in is strictly better than 1/2 by some non-negligible advantage. That's the assumption, right? So we start by assuming that there is an adversary. Yes. So the first observation, and sort of where we're going to leave the world of random oracles, is that we want to argue that the adversary will actually query this S, that like in the encapsulation game that the game encapsulated, or that this S that was generated during the encapsulation game. So encapsulation computing the actual ciphertext. We want to argue that the adversary must query this S with probability at least 2 times epsilon. Okay, so in order to do that, we're going to introduce an event, and the event is we call it hit. The event simply says the event is that that the adversary queried the random oracle. So in other words, H. Probably put H here. He queried H on S. Okay. So now I can split this probability, right? I can consider the case where the event occurred and the probability where the event did not occur. So the first observation is that if the event does not occur, right? So in other words, he doesn't query. So since K0 is H of S, if he doesn't actually query the random oracle on S, then K0 has a distribution that is indistinguishable of anything of the view of the adversary. Why is that? Because a random oracle has random entries in the entire table, right? So if I query, if there's a row of the table that you shouldn't query, that's just a uniformly random string in the view of the adversary. So the probability that he somehow correctly guesses if he is in K0 or K1, if in the 0 case or the 1 case, in the case where he doesn't actually query the random oracle, that has to be exactly 1/2. because the distribution of B is completely independent of the adversary's view. Okay. The other side, I don't know, right? Like, what's the probability that he correctly guesses the bit if he actually queries it on S? I don't know. It's something less than or equal to 1, right? It's some probability. Okay. So then I have here on one side the hit probability, so the probability that he queries, and well, this expression. Well, if you simplify it like this, then if you move all of this to the other side, you bound this by 1, then indeed you recover that he queries the random oracle with probability at least 2 epsilon. Okay. The takeaway is that the adversary must actually query the random oracle. So in other words, if he can distinguish between the 2 keys, then it must be because he knows S. That's the only way he can distinguish between K0 and K1. Is that if he knows S. Okay. So now the observation here is that the extractor is going to work like this, right? So intuitively at this point we already know that the adversary has produced S. So he must also provide a description of S. So let's see how we go about doing this. So the extractor is going to work like this. It chooses a random R, and then it basically just computes the ciphertext correctly. And then he invokes the adversary in this ciphertext. Okay. So if he queries the random oracle on S, then we'll extract. That's the next step. Otherwise, S is never queried. So then the extractor fails. But that happens only with small probability. That's which is so. So now, for some reason, right, like the adversary has basically given the adversary has basically given us this S, which is this pairing, which is equal to this pairing, right? Just because we know that when we encapsulate, we can generate a description like this, and he has also given us some description, right? Like we gave him the ciphertext and the commitment key, and from that he came up with an S. So now, because he's algebraic, he must also describe how S is derived, right? So he must describe how the commitment came about, because that part of the game he gets to give us the commitment. And he must describe how S came about. Right? Which is, so what power does he have, right? So S is some target, com is some G1 element, right? So it must be a linear combination of the G1 elements we give to him. Which is basically the powers of time. Now S, he has a little more power, right? In particular, he can take all the elements that we gave to him and he can sort of pair them with himself. So now he can compute, for instance, powers of tau up to 2D, right? Because he can pair any like pairs of elements from the setup. Again, we're doing this the security proof is in a symmetric setting. What else can he do? Well, he can take the ciphertext that we gave to him and he can try and pair that with something from the powers of tau. Maybe that's useful to him, right? So here it's like a pairing between the ciphertext we gave him and something from the setup. Maybe that's somehow useful to him. Put that here, call that Q. And then he can also take the ciphertext that we have and pair it with itself, because we're in the symmetric settings. He could do that. We'll call that scalar we call H. Okay. And yes, so what can I do? I can pull out this factor. I can pull that out. So if I rewrite everything, like I can view this all as polynomials. I can rewrite this factor and pull this out. And I can also pull this r² factor out. So now I have something that doesn't have r, like a constant term in r. I have something with a linear term in r, and I have something with a quadratic term in r. Maybe like intuitively this should have been, no, this should have been here. So, no, this should have been in front, and this should have been like a coefficient. So now I can define polynomials, right? This is again exactly the same trick. I'm basically following the same trick as I did with KZG. But there are sort of two quantities I want to be able to recover in my reduction, right? Either I want to argue that somehow the adversary that distinguishes between the two encapsulation, the encapsulation and the random key, in other words, he recovers S. The adversary that can give me an S, he must either know R, because obviously, like if I know R, I can also decrypt, because then I can basically just act as the encryptor. Or he must be able to recover tau. So exactly like I did before, I'm going to introduce variables, sort of for the quantities R and tau respectively. And tau is gonna take sort of the indeterminate for tau is going to be X, and the indeterminate for R is going to be Y. So if you go back, see here, this com is going to be some combination of these FIs with X and the correct powers of the X's. And S here is going to be, well, Y, R is going to be replaced by Y. So this is going to be Y, this is going to be X. This is going to be powers of X. This is going to be Y squared. This is going to be X, right? So I can write up a polynomial like this. I can write up a polynomial here for the commitment, and I can write up a polynomial here for S. In other words, if I evaluate this, right, in particular, if I evaluate this F at tau, I will, and I can put that inside the G1, into G1, then I will recover the commitment. And if I evaluate this G at tau and R, I will recover S in the target group. Right, if I take G in the target group and I raise it to that power. Is that clear? That's sort of the crucial observation. Okay. Now, if this bivariate polynomial is equal to this, then I'm just going to have the extractor output. Essentially, it's just going to pick out the Q part here, and I'm going to say, hey, this is actually the proof that I was looking for. Like I'm actually, I'm just going to take the QIs here, and this is actually the proof that you're looking for. I'm going to need to prove that it does, that this is the case, that like this pi actually satisfies the pairing equation. That's going to come next. And if this is not equal to this, then the extractor will fail. We have to argue that the extractor basically never fails, and so spoiler alert, in the case where this is not equal to this, I'm going to have kind of a similar thing that we had with KZG, where if I'm subtracting them from each other, it's a non-zero polynomial, and that's going to allow me to break some cryptography. So we're going to get there. But first, let's start by arguing that this pi, if I compute it like this, then this will satisfy the pairing equation of KZG. Okay. So if this is equal to this, that's exactly the point. That's exactly this. Then we can actually eliminate some terms, right? In particular, anything you see here, there's some constant term here that goes away. This y quadratic term, that must go away, right? Because like on one side, I only have y times something. I only have like terms that are linear in y. And so on the other side, this bivariate polynomial, everything that's not this term here in the middle must go away. This must go away, and this must go away. Yeah, that's exactly it. And now, if I simply take this and I divide on both sides by y times x minus alpha, well, this looked like a KZG opening already, right? So now if I evaluate both sides at tau, which I can, homomorphically do, then it satisfies then it is in fact like a completely honestly computed KZG opening. Yeah, that's exactly all. That's all. Is this clear? Yeah, this is it. Was the strategy clear to people? Okay, people still following? Yeah.
So you're like rephrasing in one sentence, the G represents kind of the right part of the equation, and the extracted part with coefficients Qi kind of represents the cross terms between the proof and the between the proof and the other part, like x minus alpha.
Yeah.
And y stands for this randomizer.
Yeah. So like this is a sort of description of the commitment, and this is a description of S, right? Like if I plug in tau here, like I can homomorphically, like if I plugged in like tau to the I instead of x to the I here, that would give me the commitment by definition. And similarly here, if I plug in tau and R, and I have, tau here in the target group, and I have R here, and tau here, blah, 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 and I have this in the target group, that will give me S by definition. And so this represents sort of the commitment, and this represents S.
Yeah, sounds good.
Yeah. And then the observation is that, hey, most of the terms cancel. If these are equal, then most of the terms cancel out, and I'm only left with this middle. And because I'm left with this middle, I can divide by this quantity, because everything else goes away. And when I divide by this quantity, well, lo and behold, it looks an awful lot like a KZG commitment. And that turns out to also be the case. If I homomorphically evaluate this thing at tau, then I will get this. This is just the honestly computed KZG commitment. And I can compute this other side. Like this I don't know how to compute, FUBA. But I can compute this, and this was actually exactly my KZG opening. So that's the observation. So if they're equal, we're good. Now, I said that the extractor fails if they are not equal, right? And now I want to prove that if this happens, then some crypto is broken. So same deal as last. I subtract the two sides from each other. This is a non-zero polynomial. It's a bivariate polynomial. It's non-zero because otherwise. Now, the trick here is that if I plug in to this is my representation of S that I got from the adversary. And this is the representation that my game computed, right? When it was like computing the ciphertext, it computed an S because it needed to like compute the key. And this is the representation that the game computed itself. So this is the representation that we computed, and this is whatever the adversary computed. And since these must be exactly the same because we recover the same key, it must be the case that when I take this bivariate polynomial, so this is basically one representation, the one that the adversary gives me of S, and this is the other representation, the one that I can compute myself. It must be the case that when I plug into Q, tau and R, I get 0. Because we're querying the random oracle on the same elements. So right, so this is S and this is S. So they're equal. So when I subtract them, that's 0. But when I subtract them as polynomials, they were not 0. So similar to the KZG case, we have a non-zero polynomial. Now it's bivariate. That has our secrets as a root. And that's exactly what we want. Okay, so now I can rewrite this Q. I can rewrite it in sort of the Y decomposition, right? So I just take all the things that are constant in Y, I put them in C1. I compute C2 as the linear term in Y, and then C3 as the quadratic term in Y. Right? Now, one observation is that these C1, C2, and C3, they can't all be 0. At least one of them has to be non-zero, because if they were all 0, then this is the 0 polynomial, and it's not the 0 polynomial. Okay, we can also define sort of the partial evaluation of this polynomial as simply like plugging in a tau. So now, if this partial evaluation is not 0, then exactly like in KZG, we have a way to recover R, right? We just factor this partial evaluation, and we recover R as a root of the polynomial. And then I guess one thing that is missing here is that we can also find a way to embed the challenge, like the QD, the LD lock that we want to break. We can also find a way to embed that challenge in R if we know tau. So we can sort of switch between like tau and R. Okay, so now if it's not 0, then so what does it mean to plug in here, right? It means that now I have a So I'm evaluating this gives me something, this gives me something, this gives me something. So I have like a little degree 2 polynomial. Oh wait, no, sorry, that comes later. So now if it is 0, so if when I evaluate this polynomial, then this thing is 0, this thing is 0, this thing is 0, right? Because if p of y, if this entire thing is 0, then the only way that the entire thing could be 0 is if this is 0 and this is 0 and this is 0, right? So in that case, I can simply recover tau as a root of either C1 or C2 or C3. Because at least one of them has to be non-zero. Okay. So it's just a little bit of an overview of like our extraction strategy. We have this probability of hit. If we don't hit, then booba. But in that case, we can show that that happens with negligible probability if you actually distinguish. And then we're in the case where we assume that we had a hit. If Q is actually equal to the 0 polynomial, we're good. Otherwise, it's not equal to the 0 polynomial, and we can either recover R or recover tau. Oh, yeah. Okay.
Matthias, sorry, I do want to tell you that there's 1 minute left.
Yeah, I think that's perfect. I don't think I have time to go through the applications. So maybe we should just jump to questions.
Maybe you could show like last few slides in a summary. That would be good.
Okay. Yeah. So one possible application that we have in the paper is what we know as like Laconic OT. So OT is this idea that one person has 2 messages and the other person basically get to pick exactly one of them. So I can pick one person has M0 and M1, and the other person gets to pick exactly one of the 2 messages, and he doesn't learn the other one. So Laconic OT sort of extends this to saying, hey, you have a set of choices, right? So for instance, it could be like you must pick 1 out of 2 ice cream flavors, you must pick 1 out of 2 countries, or whatever your favorite color is, 1 out of 2. And you commit to all of these choices, bitwise choices, and then you can compute a hash sort of all these choices, this entire database of choices that you made. And then at a later point, I can take your database hash and I can sort of send M0 and M1, such that you can only recover the correct M that corresponds to the bit in the database. Yeah, this is exactly it. You can do this for like multiple messages. It's kind of like a compressed version of oblivious transfer, for those who are familiar with it. The construction is fairly simple, right? It's simply that I just take I have an extractable witness encryption for a polynomial commitment scheme. So I'm basically just encrypting to this polynomial that you committed to at position I, evaluates to 1, or it evaluates to 0. And now, obviously, the polynomial can only evaluate to 1 of the 2 values, right? So if I evaluate the polynomial I, it can be at most 0 or 1, right? It can't be both. And so you can recover at most 1 of the 2 messages. And because KZG commitment is succinct, right? Like the commitment has the same size, no matter how many things you commit to. This trivially sort of gives you a Laconic OT. It's a very, very simple construction of Laconic OT. Yeah.
Does it mean that you are happy with the slides right now? Or you want to wrap up?
Yeah, I think that's fine. All I have is some benchmarks.
Okay. Well, let's then thank Matthias for now, and I think we have a few minutes for questions. That would be quite okay. If Matthias, unless of course you need to run this off.
Oh no, this is perfect.
Okay. Any questions? 5 minutes should be fine. Yeah. So while people are thinking, I might squeeze in one of mine. So when I was reading this the abstract and a bit of an intro to the paper before, I had some impression that this the witness encryption scheme that you provide seems much more straightforward to implement than what I imagined witness encryption schemes to be on average. And so it would be nice if you could like clarify where this paper is positioned within the witness encryption area. So does it create a simple construction, generic construction? How does it compare in terms of complexity?
Yeah, I mean, it's very specifically only for KZG commitments. So I mean, the holy grail of witness encryption is witness encryption, even without extractability, for all of NP. But those constructions are bound to be much more complicated than this. This is a very, very simple witness construction. Like it smells a lot like identity-based encryption and like these kinds of pairing-based primitives.
Okay, so as far as I understand, there is very little to no relation between the so to say expressibility power that is usually given to users by SNARKs that operate over KZG commitments and this quirk. So you literally cannot like, what is the class of languages that you can implement this WE4 efficiently?
I mean, things like linear languages, we know. I guess KZG is like an example. It's a particular example of this. Right? I think there's a few other classes, but I mean, it depends on your definition of efficient. But yeah. But I mean, maybe just to expand a bit, just like you might think, hey, now I have witness encryption for KZG. I can use KZG to compile a SNARK. Would that not give me witness encryption for anything that the SNARK can prove? The answer is no, because the SNARK will rely on interaction. Like in particular, it will rely on a random oracle. And so when you start executing your SNARK, you must know a witness. And so you can't sort of encrypt to SNARK if that was like your hope of like bootstrapping this into something much more powerful.
Yeah, like a 2-second idea that was in my head, which I realize now is not true at all, but it was something along the line, if you can prove, if you can create a witness description for the statement that like a certain commitment is evaluated at a certain point to a certain result at a certain point, so maybe you can generalize that to a set of commitments that jointly evaluate to 0 on a certain polynomial, and then maybe you can extract, and maybe you can extractability would apply to the values inside these commitments, but your extractability is not about the values of commitments, so.
No, I mean, you recover the proof, right? And then from the proof, you can apply the KZG extractor to recover the full polynomial. And you could also extend it to multiple polynomials. You can say, hey, all of these polynomials must evaluate to this, this, and this. That should be fairly straightforward. But the thing is that it's still just kind of a trivial language. Like what gives polynomial commitments their power? I mean, the language of the value of polynomial commitments is not very interesting, right? It doesn't actually give you a lot of power to prove NP relations. What gives you the power is interaction, right? And the moment you start having interaction, you're toast, because the interaction will depend on the particular witness, right?
Yeah, that makes sense.
Yeah.
Any other questions? 3, 2, 1. Okay. Well, then let's thank Matthias again. I was very happy to see the presentation. Really good one. Thanks everyone. And yeah, we meet in 2 weeks as usual.